Okay, we are now recording. Happy Monday. I like to start this class off by saying it is always very strange that we this particular class compared to what everyone else looks like. Sort of like all the rest of your classes, I feel like you've had 3 of them probably by now. So there's this whole sense of community that you have with your other courses that when we teach on a Monday, we don't tend to get because you get one class and then you go away for a couple of weeks. So I'm glad to have you back, and we're going to pick up where we left off and keep going. All right. So in this lecture today, we're talking about bivariate relations. So we're going to build on some of the information we did last week and keep going. This time, the first thing I want to have us talk about, can you see this screen? Just confirming that you can all see it. Awesome, thank you. I have a little bit of an outline here of the important topics that I want you to take away from today. I have, the first thing we're going to do is a review of statistical significance and p-values, which is what that quiz was related to, not quiz, that poll was related to. Next, I'm going to talk a little bit more about how to interpret your b-weights. We did that last week or whenever, 2 weeks ago, but I want to dive into it a little bit more today. I'm going to talk about centering your variables. That's related to the paper that I had you read for today. Fourth, I have understanding model comparisons, and model comparisons is what the whole of statistics is sort of, not statistics, the whole of regression is based on. And then interpreting this index called an R-squared index. And then last, I put it all together to sort of show you how to walk through it. And interspersed in here, I have 2 or 3 times that you'll go off into breakout rooms and meet with one another to digest and talk about and apply some of the things that we're doing. Okay, that's what today looks like. Here we go. So, starting this out by saying what I'm going to give you here is a very brief orientation to the concept of statistical significance and p-values and how we were going to use it in this class. I also have 2 readings for you on statistical significance that I want you to do before next week in a discussion post. And I realized I did not warn you that you were going to have a discussion post last time, so I want to make sure I warn you this time. And if you were not able to get to that discussion post before now, I understand. Take some time and fill it out whenever you can. So the way that I've worked this out is because I've shortened our course by an hour. I usually lecture for a full 3 hours. And so I've shortened that, and I've tried to supplement by giving you additional readings and material to do in that hour that you would have been doing during the lecture. Okay, so you'll have 2 readings and a discussion to do on statistical significance for next week. What I'd like you to do and take away from those readings is to deepen your knowledge and understanding of how p-values work and how they'll be used within social social sciences, like you're doing here. So now this is something that you should have had an introduction to in a previous course before you got to me. That's why I'm really just going to briefly go over it here. It's a comparison between a null hypothesis and an alternative hypothesis. And I think you should remember those. Sometimes you would have learned it as an H sub 0 and an H sub 1. Mm-hmm. Now, one of these is a null. Usually I'd have you raise your hands. If you think that 1 is the null, there is a difference between A. Oh God. There is a difference between A and B. Then raise your hand if you think it's A. Okay, and if you think it's B, not B. Oh God. If you think it's 2, there is no difference between A and B. Yes, you're right. Good job. Null means 0, means none. They're all related. So the null hypothesis always assumes that this value is equal to 0. So 2 would be the null. Now, what statistical significance refers to is generalization. So this is the definition of a p-value. A p-value represents the probability that you would see a coefficient at least this large as the one you've already observed if you did the study again with the same population and the same model, assuming that the null hypothesis is true. And so a p-value of 0.01 means there's a 1% chance that you would see a result or a coefficient at least this big or bigger if there really is no relation that you're looking at, or if there really is no difference between your two groups. And if you're thinking about that poll now, I'll show you the poll here. The correct answer is this one. There's a 2% chance we would get a result at least this large if there really is no difference between groups. Now I want the 48% of you who answered this one to know that this is a very common misconception of the way that this works. And I sprung it on you and you had like 1 minute to look at it. So don't feel bad. So the review of, so this is the correct answer. And these are all really common misunderstandings of the way p-values work. And all three of them are represented in one of the readings that I've given you. In 2016, the American Statistical Association put out a statement about p-values and what they are and what they aren't. And they spend actually a big majority of the article talking about what they aren't. And that's what you'll be reading for this coming up week. So you'll see what people, how people are misunderstanding them. And pointing out, again, this is in 2016, released by the American Statistical Association. So these are very common, coming out all the time. So what we're trying to correct those assumptions that you may see incorrectly in other texts. Not like your textbook, but like other published articles. Okay. So one thing that sometimes people think is that, you know, the whole thing about generalization is that it's if you're going to do the experiment or the study again. And a lot of people say, I'm never going to do this again, so why does it matter? No, thank you. It was hard enough the first time. But it's actually, it matters because that's what these statistical tests mean. It's what they refer to. Because you're trying to say, if you did the same thing, this is what would happen for you. Also, before you knock replication, it's actually a pretty common practice in some fields and becoming more and more common in education and the social sciences. People are deliberately finding studies that have been done and going back and running them again to try and see if they find the same thing. This is interesting. Yikes. Okay. So these tests tell you how likely it is for an effect at least as large as what you did see to happen again, assuming that there really is nothing going on. So it's like, if there's no differences that, or this relationship doesn't exist, what's the probability that you've just found this and it was chance? It was random. Okay. For this class, we're going to be using the criterion of a p-value less than 0.05 indicating statistical significance. And I wrote it here. You can see my cursor, yeah? This little guy? Okay. This is the less than symbol. Remember the crocodile or the alligator wants to eat the bigger number. The chompy mouth monster wants to eat the bigger number. So the P is less than 0.05. You all laugh. I've taught this class a long time. People often write this wrong. So, all right, p-value less than 0.05 indicates statistical significance. That's less than 0.05. Smaller than, closer to 0. And the meaning here is that there's a less than 5% chance that you would see a value this extreme if you did the study again, if the null hypothesis is true. So if you don't have a conceptualization of 5% chance, I like to think about it, if anybody is familiar with a D20, if you have a die that has 20 sides, if you roll it and you roll a 20, that was a 5% chance that you would roll a 20. It's also a 5% chance that you roll a 1 and critically fail at something. So you can think about it in those terms. If you've ever rolled one of those die and it's come up on one of those numbers, that was a 5% chance it would happen. So I bring that up to say a 1 in 20 chance feels really small, but it's not that small. And this is what we build our science on, for better or worse. Okay, that's my very brief overview to help get you situated and understanding how we're going to use p-values less than 0.05 in this class, and to help get you situated and oriented to the readings that you'll do for next week. I did have somebody in the discussion, I think it was Abby, who brought up the difference between practical significance and statistical significance. And I think those are really interesting. Those are really important for us to consider within the context of this, our social science. And I'd like us to keep thinking about that. What's the difference between something that's practically significant versus statistically significant? So as you're reading, you'll see some information about that within those texts, and you can think about bringing that out in your discussion. Okay. Now we're going to talk about regression. So I want to revisit this idea of the difference between correlation and regression. Correlation has no directionality assumed among the relationship between your two constructs that you're looking at. It's about the association between your two variables, whatever those two variables may be. Now, regression is about prediction. Am I from Canada? Weird. Regression is about prediction. So your variables in this case need to consider the time frame in which they were collected. So as you're thinking about your homework assignment for this week, which is going to be running a regression on your data, whatever it is, you want to make sure that your predictor variable is either measured at the same time that the outcome was measured, or it was measured before the outcome was measured. Oh, somebody's talking. And having a p-value less than 0.5 means a 95% chance. Not quite. Sorry. Oh, sorry, Jamie. I didn't see that was private. We will chat about it in a minute. I want you to read. So before you have clarification questions on p-values, I want you to read those, and then we'll open up the discussion online so that everybody can see them. And we'll move forward through there. Move forward. We'll continue in that discussion online that way. All right. So I think I have more about this. Here are some variables that can only be predictors: a person's gender identity, a person's age, a person's zip code, and a person's income. When we're thinking about things like this, you can't predict how old somebody is because they just are how old they are already. Unless you have a very specific case of like, you really need to figure out how old a person is. I don't actually know. You could, never mind. Pretend I didn't say that, because there's very, very, very strange circumstances under which maybe you might need to do that, but usually you don't. So these are all things that you can use to predict other characteristics or other variables about your sample, but you wouldn't want to predict them themselves because they existed first. So when you think about variables that could be predictors or outcomes, I picked two things at random. So a kindergartner's reading score or ratings of happiness. You could also have something like a quality indicator of a classroom or the number of times a teacher uses a particular strategy. All of those things could be dependent on things like gender identity or the person's age or their income or their zip code, but you wouldn't expect the opposite to be true. In a correlation, that doesn't matter, but in a regression, it does. So now I want to talk a little bit more about the regression equation that I showed you last week. I'm going to keep saying last week. I mean 2 weeks ago, every time. So here, we're digging right into an example. So here I have run a regression, and I'm predicting a student's SAT score. That's the high school exit test. And I'm predicting it from their high school GPA. High school GPA ranges from 0 to 4. Sometimes it can go up to like 4.5 or something like that, depending on how things are scored. And here is my SPSS output, or my model results. And we're going to focus on these B weights. These are our unstandardized weights, our coefficients for our regression equation. And we can harvest these and put them into a regression equation. And here is how I'd harvest them. I have rounded them for ease of math. So I've harvested my intercept, my y-intercept here, as 355. And I've harvested my x value, and I've rounded it up to 300. So my predicted y-score for each person is equal to 355 plus 300 times whatever the x value is. I just told you what the y-intercept is. It's 355, and I pull it from here. And I've just told you where the slope is. It's 300, and I've pulled it from here. Now with the significance tests, oh my God, I need a hat. With the significance tests, remember we're going to read across the line. So the statistical significance of the intercept is here. So this is telling us that this number, 355, is not significantly different from 0. Whereas this right here, this coefficient, the slope, 300 is statistically significantly different from 0. So we're saying the null hypothesis here is that GPA is not related to SAT, and the alternative hypothesis is that it is related to SAT. So here we reject the null hypothesis that GPA is related to SAT scores, and we say, so GPA is related to SAT scores, and that number is significantly different from 0. I'm going to do that a lot, so stick with me. I have boxes. Dun, dun, dun. So what we can do with this regression equation we've just gotten, remember I harvested them from here, and now I'm going to show you what we can do with these. You can use this information to get a predicted y-score for any value of x, any at all, using algebra. So what is the predicted y, the y hat, if GPA equals 0? And what is the y hat if GPA equals 1? I want you to take like 3 minutes and see if you can estimate what's hidden underneath here. Write the regression equation and figure out what the y hat is if GPA equals 0 and if GPA equals 1. And I'm going to I'm going to just time you. So I'll give you 3-4 minutes to do this. Okay, that's 1 minute left. Okay, now I'm going to ask for a brave volunteer to step forward, unmute yourself, and walk us through this first equation. What is the y hat if GPA equals 0? We've got Shantu.
Yeah, it's me.
Yeah.
Okay, so if y hat And so y hat will be 355 plus 300 into 0, which is 355. And for the second one, it'll be 355 plus 300 into 1, which is 655.
655. Yep, exactly. Do you see how we have this here? The multiplication of 300 times 0 gives you 355. And 300 times 1, which results in 655. So, and the interpretations here are when GPA equals 0, we expect SAT score to be 355. And for this one, the way you'd interpret that is when GPA equals 1, we expect that SAT score will be 655. Okay? Knowing that, can you interpret this? Hold on. Oh gosh. I have just run a regression based on my situation this morning when I was working on these slides, which is, oh, that's the next one. I've run a regression predicting the number of sales at my local ice cream shop based on the daily high temperature. That was not my morning. Today's daily high temperature was very cold. So the number of sales at my local ice cream shop is predicted from the daily high temperature. So take about 4 minutes and try to answer all of these questions on your own on a piece of paper. Timing you again. Eventually. And if you're done, just send me a private message. I'm trying to figure out how to, because I would ordinarily have you like put pencils down when you're done or put your hand on your head. That'll work. Just send me a message and then I'll see.
You can also, in the participants window, there's like a yes and a no answer. So you can always have people answer on there and like click yes when they're done.
Doesn't that show everyone else that you're done?
Yes.
Yeah, that would work. Use the participant tab here. Okay, that timed out pretty well. Okay, so I'm going to send you the answers on this one. The Y value here is the number of sales at my local ice cream shop. The X value is the daily high temperature. And if I'm interpreting 3150, 3150 is the number of sales when the daily high temperature is 0. And if I'm interpreting the 17.9, it's the number of sales for every degree Fahrenheit increase or degree increase in temperature. So every degree warmer it is, it's 18 more sales in my ice cream shop. Okay, we're going to do it one more time. This next one is based on what happened to me this morning, which is a regression predicting the temperature of my coffee in degrees Fahrenheit from how many minutes I let it sit still and didn't drink it. So in this one, what I'd like you to do this time, it's the same basic question. It's just with slightly different numbers and different Y and different X values. I'm going to give you 2 minutes to work on it on your own, and then I'm going to put you in groups together to go over the answers that you have thus far and to help one another through that logic. So your 2 minutes starts right now. Sorry. Okay, we have time up. Oops, sorry, I didn't mean to do that. Okay, well, I'll bring that back in just a second. I have time up. What I'd like for you to do is I'm going to send you to your breakout rooms, and I'm going to give you about 5 minutes there. I'm really torn because I want you to chat with each other and introduce yourselves if you haven't met each other yet. So I'm going to actually give you longer than that. So I'm going to give you 10 minutes to chat, and I'm going to give you 10 minutes to chat. The first 5 should be introducing yourselves, and then I'm going to give you another 5 minutes to talk about the results. And are you ready? Okay, go. Your word. I'm not making it through this today. There's no way. Oh, I think I just broadcast it.
Hi.
Hi, I'm just jumping randomly in rooms to see what's making sense and what isn't.
Yeah, we just went through all the questions just now, and
Great.
there was consensus.
In
This
a
is the
good
this
way.
is the simple part, Dr. Logan.
Oh,
You give me the good stuff that make me seem like I actually feel like I know something when I don't feel like I do. Like even with the poll question, I was like, "Oh, wait a minute, I got that right." I was like, "Wait, look at me thinking I know something when I'm like a chicken with his head cut off and everything else."
well, that's one of the reasons that I like to do it this way is we start off really slowly with the idea that you get these confident things under your belt. You get really familiar with them so that you can move forward. And this is like all regression is. It's just going to get a little bit more complicated every week.
So
Yeah?
I have a question.
Okay.
Example of whatever. So in this instance, right? What happens? I didn't go far in the math, but what happens when this starts going into negatives? Can something go into a negative degrees?
So that's a really good question. And I would love to
Or
hear you think about that.
like, because at a certain point, like the coffee is only going to get. I'm not a scientist, so don't get me to talking about the science of heating and cooling and all of that good stuff. But at a certain point, obviously, if I say I let this sit for I've seen amount of minutes, 1,000 minutes, it's
Oh, that is really interesting.
having a temperature that's below zero, and I don't think that that's. I mean, in a world like it's not going to progressive like it's going to get to a certain point where there's like it's not going. Maybe I'm thinking too deep into this.
Nope, not at
But
all.
there's no level because like one, there's no level of consistency to know. Like there's so many other things that I got to consider when this temperature is dropping. But
Uh-huh.
at some point with this model, it's going to get below zero, and I don't think that that's humanly possible. If something is just sitting still, unless
Yeah.
you're in a very cold room, but even still, it's going to eclipse at some temperature.
What do you two think?
Would like, I don't know if regression would cover it, but maybe it wouldn't be a linear regression. Then it would be some other type of regression if there isn't like another type of regression that can like get into like asymptotes, I guess, in this sense, where it just like plateaus off. Yeah.
Uh-huh. That's exciting that you know what that is. That's very cool. So yes, I think you're exactly right. And I think what you're highlighting there is the limits of what regression can and can't do. So we would never expect, even if I had 100 cups of coffee and I had them in 100 different rooms, depending on the temperature of that room, eventually it's going to bottom out. It's not going to get any colder. But you could also think about that with anything else that you study. So try and translate that idea to whatever it is that you're thinking about in your particular area. So like I had a student a couple of years ago who studied ticket sales at Ohio State games. There's a cap on those ticket sales. You can't sell more than a certain number of tickets. That's just the end. And so it doesn't matter how good your prediction is, eventually you're going to hit an asymptote, like you said, Monica. So I think regression's really good for talking about predictions within a particular observed area, but outside of that, it's really limited. Otherwise, we would have, that would be a really nice way to invent energy. All right, it looks like our time is up. I'm going to send us back. Thanks for letting me chat with you.
Thank you.
Thanks.
Oh, there she is.
Hi.
Hey,
Okay.
Sorry. How are
No,
you?
you said we were a little concerned that we came back in the main room and we're alone.
Oh no, sorry. I was visiting breakout rooms.
Okay.
I'm gonna stop. Go away. Okay, I'm gonna end breakout rooms because our time is up. Did you all solve it? How do you feel?
feeling great.
Aw. Logan and I have known each other a long time. It's fun to hear your voice, Logan.
It's fun to be in your class.
Aw. Are we back? Oh God. Okay. There's so much technology and it's just great. I'm glad we all have it. Okay, we have not everybody back yet. You reminded me, I visited one of the breakout rooms and we were chatting about the limits of regression and what you can and can't do with it. So that's one of the first things I want to talk about. I'll have a couple of other readings for you this week that are pretty short. The question was, well, I'll get there. Hang on. So looks like we have everybody back. Okay, so from the people who are back now, did Anybody end up with fuzzy points or weren't sure how to answer one of these questions within your group? No shame, if so. Okay, so how hot was my coffee right after I made it?
190.
190 degrees. Yeah. Oh, yeah. Cool. Answer in the chat. Oh my gosh, that's so fun. Okay, answer in the chat. Does the coffee get hotter or colder as it sits still? It gets colder. Now, that one, if you didn't get it from just like, you could have gotten it hopefully from common sense. Everyone has probably sat with a cup of coffee or tea in front of them at some point. It does get colder, as indicated by this negative sign in front of the 0.03. I'm sharing this, right? Am I not sharing this? Dang it. You're just looking at my big old face. Gracious. I love technology. I really do. Resize window. Okay. Thank you for answering. I appreciate it. And then the last thing I have here is how much the temperature changes per minute. And the answer is it decreases by 0.3 degrees. I have no idea if that's accurate and how fast things cool. It's not accurate, I have been told by several people shaking their heads at me. Okay, so now the question that came up in this was, but what if you leave it sitting overnight? What if you've left a cup of coffee on your desk and you go to bed and you come back the next morning and it's there? Has it continued to decrease at the same rate for that whole time? Definitely not, because otherwise you'd come back with a block of ice on your desk. So there are some limits to what regression can and cannot predict. So it can only predict within the range of actual observed values and within the range of observed possibilities. I'm going to give you 2 really short readings on that as well, which I'll put in another, like in the reading section of your weekly thing. What's it called? Module. Oh, gracious. All right, so I'll put those in there as well that you can look at. Next. Okay, next we're going to talk about centering. So if this is making sense, that's really good, because I'm about to make it a little bit more confusing, which is just like the theme of the class. Glad this is making sense. Now we're going to make it more confusing. Okay. So centering is about that intercept article that you read. Now that intercept article is a lot of details, but I'm talking about sort of the basic idea behind it, which is the idea of centering and what centering can do for you conceptually. Centering variables just means moving where the 0 is. And it's usually done so that our 0 is a meaningful number. In our GPA example, we were looking at expected scores when GPA equals 0. But the thing is, this is problematic because that data set is really small and it doesn't have anybody with a GPA of 0. And the possible range of SAT scores starts at 400 and goes to 1600. So if we end up with a predicted score of 355, that doesn't make a lot of sense. Even more so, it doesn't make a lot of sense because we're trying to predict for people who don't exist. We don't have anybody with a GPA of 0 in our model, just like we don't have any cups of coffee in that example that got left for 24 hours. So you would use centering in instances where you need to make your intercept more interpretable. Later on, you need it to make other coefficients more interpretable. But for now, you really just need it in order to make your intercept more interpretable. And I'll show you how that works. So here is that output that I showed you a minute ago. This is GPA with a coefficient of 300, and our y-intercept here is 355. We have really talked about that a lot, but we know this B0 is for people with a GPA of 0, which doesn't make sense for our data. We don't have anybody with a GPA of 0. So we're going to center GPA, and I'm going to choose to center it at the mean. In order to do that, the first thing we have to do is figure out what the mean is of GPA. So I ran some descriptive statistics and I found that our mean is 3.07. So I'm going to recenter at 3.07. And the way that we do that is just ridiculously easy. It's conceptually very confusing, but it's very easy to do. You subtract 3.07 from everybody's score. So I'm going to create a new variable. It's a new GPA variable called GPA at the mean. And I'm taking the GPA variable and I'm subtracting 3 from everybody's score. And then I'm going to rerun the analysis using the new GPA variable. Don't worry about this regression code. This regression code is here for you later on once you've learned how to use it. You haven't learned how to use it yet, you'll learn tomorrow. Then you'll come back and get to use this code. For now, I just have it here so you can understand it later when you review your notes. All right, so now I've recentered my variable. So now a GPA mean of 0 means my GPA is 3.07, which is like, what? But that's what it is. Which means now the average SAT score when GPA mean equals 0 is 1275. Because when GPA mean equals 0, student GPA is 3.07. So it's like a 2 steps removed process. I want to do it again. So this is the same thing we did before. We're still going to use, we can still use a predicted value, still use a value of X to get a predicted value of Y, but we have to interpret it slightly differently when we do it. Because when X equals 0, now X really means 3.07. X doesn't mean 0 when it says 0. It means 3.07. Okay. So what's the predicted Y if GPA equals 3.07? In order to figure that out, we have to think about plugging in for the X value. What? We have to plug in a specific number for this X value that represents when GPA equals 3.07. And that is 0.
0. Yeah.
Yeah. So in this case, when GPA is 3.07, I'm going to plug 0 in. And I get 1275 plus 300 times 0. So 1275 is my predicted value. And so I would interpret that like this. When GPA is 3.07, or when GPA is at the mean, my expected Y score, or my expected SAT score, is 1275. And so here, if I'm looking at a GPA of 4.07, that is 3.07 plus 1. Yep, so it's going to be 1. Oh, yeah, I can see the chat is blinking, but I can't see it anymore. It's disappeared on me. I'll find it. So I plug in a 1 here, just like I did in the last equation, but this time instead of it meaning 1, it means 3.07 plus 1, so 4.07. So this is how I would interpret that. So that's the basics of centering. So now, remember before we were getting predicted scores of 355, which didn't make sense. Now we're getting scores that are within our range of observed values, like our coffee cup has been sitting for 20 minutes, not 20 hours. So we have an observed value within the range that makes sense here. So we're predicting within the range that makes sense as well. Now I want you to try. Here is my example question. I have used child. That's just talking too long without vocal warm-up. That's all that was, not coronavirus. Okay, I've used child age in months to predict their vocabulary scores. And I have, in this example, I can imagine I have 100 kids. And if I have child age that's ranging from 36 months to 72 months, and I have vocabulary that's ranging from a score of 55 to a score of 160. I centered age at 36 months, which means 36 months is equal to 0. And then I have a resulting regression equation of y equal to 58 plus 1.3 times x. Can you tell me the following two things? What's the expected score for a child who's 36 months old and the expected score for a child who's 72 months old? See if you can figure out how to do that. You've got 5 minutes to think, and then I'm going to put you in groups again. Okay. looks like our time is up here. So before I put you into rooms, oh, I can't see you all anymore. Where'd you go? Okay, before I put you all into rooms, are there any, there's my kid. You want to say hello? He's about to
Hi,
go to
Charlie.
soccer practice. Before I put you back in rooms, I had a couple of quick questions on the side, which I can't, here we go. So that I wanted to make sure I acknowledged. If you are like super lost and this is making absolutely no sense, just type me a little like, I don't get it, and I'll come visit your group here in a second and let you know. And I'll chat it through with you. Okay. I'm sending you back to your same rooms. You've got about 4 minutes in there, and I'll see you in a minute. Okay, Chloe is in which room? Hello.
Hi.
Hi.
I hear tell that you think you need help.
We definitely need help.
Okay, well, I'm here for you. Do you understand the premise of question 1? That's a terrible question. Let me ask it a different way. How did you go about trying to solve question 1?
So when you were talking about the first example with GPA, you said when you move to 1 instead of 0, it's now 3.07 plus 1.
Uh-huh.
I got lost after that. I don't know how to deal with 36
Sure.
and 1. Like, does that make any sense?
It does make sense. So let's think first about what, were you two both, Fen and Sarah, were you both in agreement on that?
I am
Not
in
quite.
agreement, but probably further behind even than Chloe is. I just feel very confused in general.
Okay.
So yeah.
I understand. I know how to do it, but I don't quite understand why we do that. Because I know I was trying to figure out the first question by let x equal to 0. And
Yes, in this right here.
yeah, and then I got the y height equal to 58. So that's my answer for the first question.
So I'm going to stop you right there to say
Okay.
that that's exactly right. Okay, so why don't you explain your thinking behind that so that we can get Sarah and Chloe to hear your thinking behind that, and then I'll supplement as needed.
Okay. I understand that as because most people have the GPA of 36, so like we set it as a baseline. So like we let it be 0.
Yes, we've converted it to 0, perhaps, and it's age in this case, not GPA, but age.
Oh, so
that's weird.
Oh yeah, right. It should be age. So I don't like why we use 36. Is it a number we already know, or we need to figure it out? Like,
so I made 36 be equal to 0.
Okay.
Yep, okay, I'm going to go help Erin in a second too. So I made 36 equal to 0 because it was the lowest range of my ages. If that makes sense. Oh, you can't see what I'm pointing at. 36. So my range of ages was 36 to 72 months. So 36 was the youngest child. So I recentered age. Instead of being age in 0 months, which would be an infant, a baby, I made age be 36 months. So when I say 0 months, I mean 36 months, which is why on that slide it says 36 months equals 0. And so if I want to know how old someone is at 36 months, then I plug in a 0 to that X value. because that 0 represents someone who's 36 months old.
Mhm. Got it. So 36 is a real age of child, and 0 is like the statistical number we use in this formula. Right?
Yes, to make this happen. And the way that you would do this is within your sort of your data sheet, your spreadsheet, where it said 36, you'd have each person has a value for this. You would take that value and subtract 36 from it, and you'd get the final result. So someone who was 37 months old, they would have a 1. Someone who's 38 months old, they would look like they were a 2. And someone who's
is that how
40
you
months
get
old would look
1
like they're
then?
4. What's that, Chloe?
Is that how you get 1 then? So if we're looking for the next, so you just subtract 36 from whatever age that you're looking for?
Yep.
Oh, okay.
That's exactly right. So now you know that. I'm going to let you note that down. See if you can solve 72 months.
Mhm.
So start with 72 months, see if you can solve that one. And I'm going to go help another breakout room, and then we'll chat again when we go back.
Sounds
Okay.
good.
Bye.
Ah,
Hi,
you
everybody.
appeared. Hello.
This is so cool. I love that I get to talk to all of you. It's just, it's great. Okay. Talk me through, how is your thinking going on the first question?
Yes.
Good. We feel solid.
Better, yeah. We feel good about it.
All right. So what's your answer for question 1?
58.
Good. Yes. Let me actually ask, tell me what's going on. How's it going? What's up?
So the second question was where we were a little misty on it. In my thought process, I was thinking like, 36 is equal to 0, and 36 plus 36 is 72, so that would be 1. So that's what I initially did. But then Ariana was like, oh no, it's by month, so 1 would actually be 37 months. And so when we did that, then we got 104.8. But we just wanted to confirm that.
Yes.
We weren't totally confident.
Ari, you have it right. It's what
Okay.
your units haven't changed. It's
Yeah.
just where the 0 is changed.
Okay. Yes,
And
that
so-
makes so much sense. We just wanted to.
Oh, great.
Make sure that it was like, because we were like, I was explaining it, and then I was like, oh God, I hope I'm not explaining like the wrong thing. And like everyone's just gonna be led astray, including myself.
Oh, I have had that conversation 4 times already today. So yes, not in just this breakout session. It started at like 8 a.m. Okay, I'm gonna call everybody back then, and we'll walk through that. Okay, thanks.
Thanks.
Thank you.
Hello again. You all are very fast. Or are you just really uncomfortable in a breakout room? Do I keep sending you to a room that has like smelly curtains or something?
Yes, that's what it is.
Okay, I'm going to call people back. And while I'm doing that, you tell me, how did it go?
It went great. We got the right answers. I think that was the goal.
Oh, yeah. Did I have the right answers on here?
I don't know. Hey, can you add me? I know you have a million things going on, but can you add me to Carmen if you remember?
Yes.
Thank you.
I have my Post-its. Okay, adding Logan to Carmen. Now, so we had a couple, oh, hi everybody. This is great. I will go through the answer to question 1. So for question 1, we're looking at the expected score for a child who's 36 months. And for a child who's 36 months old, the value we would use for X to represent someone who's 36 months old is 0. And so our predicted score for somebody who's 36 months old is 58. Now to get to 72, remember I subtracted 36 from everybody's score. So I end up with 72 minus 36, which I think is 36. So then I would plug 36 in for the X value here. In which case I have 36 times 1.3 plus 58 gives me my predicted score for somebody who's 72 months old. And this is just, it just feels so confusing. And I understand that it does. So I wanted to clarify two things. First is it helps to think about this if you're going to use centering in your data. If you remember the assignment that you just turned in, I asked you to document whether or not you have a 0 represented in your data set in that variable. This is the reason why I wanted you thinking about whether you have a 0 in your data set. Because a lot of variables, like these ones we're looking at that go from 55 to 160, or age in months from 36 to 72, if you're trying to predict something that's happening around 0, which is what all regression does, then you're going to be ending up interpreting things way outside of the range of observable data. And so thinking about centering can be really helpful to you as you're considering how to analyze your own data sets. You may want to move around where your 0 is, and you do that through subtraction. And so I encourage you to play around with this a little bit in the next time you're looking at your data. So if you take the way that you would look at this would be to conduct that subtraction and then look at both of those columns of data to sort of look at what does it mean to have, if this kid is 36 months old, now they're a 0. This kid who is 37 months old, now they're a 1. So looking through that data may help sort of sediment this idea in your head of how it works. And I got a really good question, which is, how is this different from z-scores? And the answer is, it's different because the number of units is still the same as it was before with these, whereas it is not with z-scores. So with a z-score, you're always talking about a 1 point change and a standard deviation increase. So a standard deviation is always 1. And in this case, we were looking at months, and it stays in months. We're still a number of months in months. A lot of times I said months. We're still talking about how many months it took for something to happen, not a standard deviation. All right, so that's the big difference between those two things. And now I'm going to move on and talk a little bit about regression rules. So the goal of regression, as we've said a couple of times, is to get a predicted y-score for each person. The rules about that predicted y-score is that the predicted y-scores should be as close as possible to the actual scores as you can get. The average error between the predicted score and the actual score should equal 0. That means we don't want to consistently be guessing too high for everybody or consistently guessing too low for everybody. And the squared difference between the actual and predicted scores should be at a minimum. And I'll tell you why it's the squared difference in a second. We always have one independent variable and one dependent variable in something called a bivariate regression. It just means 2 variables. And you're doing a bivariate regression for homework this week. Now we know what that x value means and we know what the b value means, but we don't know if we've done a good job predicting the data. The regression procedure provides us statistical tests to tell us how well our line fits the data that we've observed. And it does that by comparing 2 models. It uses a model comparisons approach. You have a restricted model. It's also sometimes called an empty model. And an empty model is a model with no predictors in it. And if you have no predictors, you just pick the mean of y for everybody and pretend that that's the expected score. I'll show you what that looks like in a second. The other model you have is a full model. A full model is full of predictors. In our case, it's going to have just 1 predictor, but it's full. And the regression equation is used to compute an expected score for each person using those predictors in the full model. So we're going to compare the restricted model to the full model to get our estimates of model fit. So if I have 100 people and I know how tall everybody is, and I want to guess how tall everybody is, that's my y, and I don't know anything else about them, my best guess is the mean of the sample. So across all the people, if I've chosen the mean of the sample, if I've guessed the mean as being everybody's height, I'm going to be off. I'm going to be wrong for just about everybody, first of all. But the errors are going to sum to 0. I'm going to overestimate some people and I'm going to underestimate some people. So those errors are going to sum up to be 0. And so my prediction isn't biased in that way. And if I translate that to our example we talked about last week, which is the number of publications someone has, and predicting that from their years of experience, I'm going to show you what that looks like. If the only information I have is the number of publications a scientist has, my best guess at the number of publications any random scientist has, any one particular scientist has, is to take the mean of all scientists for whom I have data. To figure out if the model fits, the first step I'm going to do is estimate how much error is in that model when I use the mean as the predictor. So here's my data. I have 15 data points, 1 to 15. Here are their number of publications, and this is the mean number of publications that I have. So on average, these 15 professors have 7 publications. So what I'm going to do, this is my Excel document here. My expected value for everyone in this restricted model or empty model is the mean of publications. So I'm plugging that in this row. Next, I'm going to subtract the mean from everybody's publication. And you see this person, I'm off by 5. This person, I'm off by 13. But if I take this and I added them all up, they would all sum to 0, because that's the definition of what a mean is. That's also called a residual. Remember when we talked about residuals last time? Vocabulary words. Okay, now the next thing I'm going to do is I'm going to square it. Okay, because what happens when I square this, first of all, I get rid of the negatives, which is nice. Now everything is in an order of magnitude. It's in like absolute magnitude. So now I've gone from negative 5.6 to this sort of absolute value of my error. How far off was my guess? It was off by 31. Now what I do next is I'm going to sum up all of these errors. When I've added it all together, I get 369. And that is called the sum, because I added it, of the squared errors. Have you heard sum of squared errors before? And tuned out that word because it sounded scary, because it's like, that's a lot of math words. It's just adding together all of the errors that you squared. I love vocabulary. Statisticians are not creative. They really are not good at coming up with creative names for things. It's like, this is not the Daphne, it's the sum of squared errors. Okay, so the other thing I'm going to point out here in a minute is that not only does this get a mean or a sum, you can get a sum of the squared errors, you can also get a variance of the squared errors. Do you remember calculating variance from intro stats? All right, so we can get a sum of the squared errors and we get a variance of the squared errors, and both of those are going to be important in terms of how we evaluate our model fit. Now I'm going to show you what this looks like. This, I'm guess the mean for everybody. I'm going to show you. Later on, I'm going to use the number of years of experience each person has. So I'm going to create a scatter plot that's years of experience by publications, but years of experience is not in this model right now. So here I have the years from PhD on my x-axis. I have the number of publications on my y-axis, and this here is the mean that I've guessed for everybody. Dun, dun, dun. It was like 7 point something. And here are my errors, my residuals, these red lines. Each dot is a person, and they are plotted based on years of experience and the number of publications. Again, this line right here is completely ignoring the years of experience. It's just guessing the mean for everybody. So this was that residual of 13.4 that I looked at before. And if I square it, then it's a lot bigger than that. So that's what it looks like when I've used an empty model or a restricted model to predict everybody. I've got a lot of big errors. I've not done a very good job of predicting everybody's scores. So the next thing I'm going to do is I'm going to add a predictor that will make it a full model. And the goal of adding this predictor is to reduce the amount of error in my model. So I'm going to use the regression equation to come up with how to do this. If you remember this guy, which you should because we just went over it for the first hour of class, we derived it to be this. We have 0.468x plus 0.311 plus error. So this is our full model. This is what we get when we run a regression with these data. That's our x variable is number of years of experience, and our y is the number of publications. And I'm going to see how much error is in our new full model. And I'm going to do it exactly the same way I did before. So again, I have each of the 15 people. I have their number of publications, but now I also have their time or their number of years from PhD. And I'm going to calculate the expected score. Instead of being the mean for everybody, I'm going to calculate it based on that regression equation. Remember how I said you could use any x value in the whole wide world to get a predicted y score? And that's what we're going to do right here. So we're going to plug in everybody's observed values. So for this person, it's 1. So I'm going to take 3.11 plus 0.47 times 1. So that's 3.58. Oh, look at that. Oh, I forgot I did that. That's for ID number 1. Here it is for ID number 2. Their value is 2, so I plugged in a 2 here for time. For ID 3, I'm going to plug in a 5 for time. Okay, and once I've done all of that, I get everybody's predicted scores. Y'all, in the old days, I would have made you do this by hand. And you would have done your first couple of regression assignments all by hand, calculating it like this. So you're welcome. Then you get the residuals like you did before, which is the predicted score, the observed score and the predicted score. You take the difference between the two. And then you get the residuals. Then you're going to square them because our residuals are our errors. And then we're going to sum the squared errors to get our total error in this model. The sum of the squared errors is 197 if I added all these together. When I'm asking you what stands out for you here, what I'm asking you is, do you see anybody who we've done an especially good job predicting or an especially bad job predicting? Feel free to throw something in the chat that you observe. Yeah, crushed it on ID 2. Absolutely killing it. And 3, not so shabby either. Look at this, super close. Wow, did we really suck at 12? We do not understand what's happening with this person at all. Yeah, absolutely true. So from here, I want to show you a plot. So here's that same plot we looked at before, where, too many things, where this is the mean for everybody. And this is our new regression line that we've just estimated based on the regression equation. And the red lines are the residuals. So here's how far this guy was before. And here's how far it is now. See, the red line is where it is now. And it used to come all the way to this black line. So same here. This one used to come all the way to here, but now it's only coming this far. So we've reduced that error by this much. I would point to it if I could. I need 2 hands. Okay. So because I needed 2 hands, I have this little guy that I've made. So here is our residual value. As an example, this little blue thing. There's the mean of y. So this right here is the variation in the model I've explained by including x. And this is what's left over. So before in the restricted model, this point had both this blue line residual and this yellow line together. Whoa, that summed up to be the total error. But now in this new model, it's just this blue line. So I've explained this much of the variability of the error variance here. So I've reduced the error for this point by that much. So that's the concept of what reducing error sort of looks like. It looked pretty bad. We added some predictors. Now it looks a little bit better. So next what we're going to do is compare the two different models to see which one has less error. Now we can look at the sums of squared errors, and we see that in the restricted model, that model with no predictors in it, we had a total sum of squared errors of 369. And in the full model, it was 197. So eyeballing it, you'd say that went down. But as we know in statistics, we want to know, is it less error? Well, obviously, but is it significantly less error? That's what we really care about over here in quantitative statistics land. So in order to answer whether it's less error, we need some degrees of freedom, which I think you'll remember from all the lookup tables that you did in intro stats. So that's what degrees of freedom are. So let's find out how many degrees of freedom we have in this model. The number of degrees of freedom is always equal to the sample size minus the number of coefficients you're estimating. In our case, in our restricted model, we have one parameter to be estimated, and that one parameter is the mean of y. Mean of y, because y hat equals the mean of y. Remember, we drew that one straight line. Now in the full model, y hat is equal to b1 times x plus b0. So now we have two parameters we're estimating. We're estimating a b1 and a b0. So for our degrees of freedom, in our publications example, our sample size is 15. The restricted model looks like this. So the degrees of freedom for a restricted model is always n minus 1 because we are estimating one parameter. So for our restricted model, the degrees of freedom is 14. And for the full model, it's always going to be one predictor. Well, in this instance where we have one predictor, it will always be n minus 2 because we're always going to be estimating a coefficient to associate x with our y and our intercept, our y-intercept. So that's two coefficients. So in that case, the degrees of freedom from this model is 13. So this is really useful information for when you're reviewing papers later also, because sometimes people, if they include their degrees of freedom, you can figure out what kinds of analyses they've run. Just as an aside. Don't freak out. I'm covering it up. You can't see. Don't freak out. It's really easy to understand. I'm going to walk you through this whole thing. It's just a lot of letters and it looks like a scary equation. But it's going to be okay. I promise. So we have a significance test. Remember, the whole point of this is to get a significance test to determine whether we've done a good job of reducing the error in our model. This is sums of squared errors from the restricted model. Remember that? Adding together the errors that we squared in the model where we guessed the mean for everybody. This is sums of squared errors from the full model. That's again adding together all of the errors from when we included our predictors in the model. And we know this, degrees of freedom from the restricted model was 1, and from the full model was 2. So this is going to be a denominator of 1. So that's easy. And then we're going to express that as a function of the sums of squared errors from the full model, which we just talked about what that is, and the degrees of freedom from the full model, which was 13. And that, once we've calculated that all out, we get an F test for statistical significance. And then we know if we did a good job predicting our model and reducing our error. Woo! N minus 1 for, yes, it was 14. Wait, degrees of freedom for the restricted model is N minus 1. And degrees of freedom from the full model is n minus 2. So it's n minus 1 for each of the predictors. Not predictors, each of the coefficients we're estimating. Girl, you better not auto start my computer right now. Okay, it's okay. We have time. We have time. All right. Now, this whole part right here, the difference between the restricted model and the full model, that's what we're doing. This is the reduction in error that we get by adding the variables to the full model. That's what we're estimating here. That's how much error did we reduce? The sums of squared errors from the restricted minus the sums of squared errors from the full. How much did it go down? And we're expressing it as a proportion of the error in the full model. Okay. Now, all I've done is pull these numbers that we've already calculated and plug them in here to show you that this here is the reduction in error variance, which gives us 172.5. And we're dividing it by 15. And that gives us our F value of 11.386. And then I looked that up in a table in Excel, and it tells me that that's P less than 0.005. Now, another important thing to notice here is the degrees of freedom and how you express them. So the way that you talk about an F test and report it is to have an F value, and then you have the difference between your restricted and full model is the numerator of your degrees of freedom, 1, which was 1, because in the restricted model, we're estimating just the mean, so that's 1 parameter. And in the full model, we're estimating the intercept and the slope, so that's 2 parameters. So that's degree of freedom here is 1, and the degrees of freedom for the full model is 2nd, and that was n minus 2. So this right here, this little F guy, is going to show up in your results tables when you're explaining to the reader what you found and whether you've significantly reduced the error. So here is an output from SPSS, which you'll get more familiar with tomorrow in your lab. And I'll show you where you find those numbers. Look at that, 197. That's from our full model. Dun, dun, dun. They call it residual in SPSS because it is about how much residual is still left in your regression model when you're done with all your full model. This right here, 369, you might remember as the number from the restricted model. This is always going to be the biggest model because you've done the worst job at predicting the outcome. And then this guy right here is the difference between the restricted and the full model. And you see, just like we were reading the other ones, the significance test here is only for the difference between the two. So we're looking at, is this reduction in error variance statistically significantly different from 0? And that answer is yes, it's different from 0. Yay, we reduced the error. And so the interpretation of this that you can use, you can copy this and paste it into every publication you use forever and ever, is we have significantly reduced the amount of error by including years since PhD as a predictor of number of publications. Woohoo. Okay. So we did it. And we know how much we did it. This F test is for that change in error variance from the restricted to the full model. I already said that. I just highlight these in another way here because I thought it might have been confusing the other way, and maybe you like these colors better. So here I have the restricted model, I have the full model, and then the difference is the regression model. Now, the other way that you think about this, that you can think about this, is variance accounted for. So we can also calculate how much variance we've explained in Y by including X. And so thinking about it conceptually, it's like a Venn diagram where I have a Y and I have an X, and we're trying to figure out how much of the variability in Y overlaps with X. So remember, I promised you that we'd talk about those variances for the error terms. Now we're going to talk about the variances. Dun, dun. When you've done a better job at guessing people's X values, they not only do your errors get smaller, but they also get more similar to one another. So before, remember, we had somebody who was like a 36 and somebody who was an 80 and who was somebody who was a 2. Those are really far apart numbers. Then once I've used my predictors in the model, those error variances get smaller because my numbers are more similar to one another. My guesses are more similar. And so to determine how much more similar, we're going to calculate another statistic using the same idea, but it's called an R squared. And I bet you've heard of an R squared. Did you do R squared in intro stats? Give me a little thumbs up reaction if you've done R squareds before. Okay, so you've interpreted R squareds, but maybe not calculated them, or maybe some of each. Got some of each. Okay, so then I'm going to go real fast through this. So the R squared is the reduction in error variance from the restricted model to the full model. And it's expressed just like our sums of squared errors were, our F-test. It's expressed as a proportion of the total variance in the restricted model. So we have, oh, it's actually backwards, because in an F-test, we express it as the total variance in the full model. And with the R squared, we're expressing it as a total variance in the restricted model. Yeah. So in our example, our variance we had from the full model was 13, and the variance from the restricted model was 24. I had those because I calculated them in the Excel sheets where I had the sums of squared errors. Underneath that, I had the variance estimates. That's where these come from. If I plug these numbers in, I get my R squared value of 0.467. And you will see that that number is right here. The proportion of variance in Y that's explained by X. Dun, dun, dun. That's another number that I want to see included in your assignment for next week. Oh, don't even. I'm just not even going to talk about that. All right, now, visualizing variance accounted for. We have the total variance in Y is 1.0. The amount explained by X is this R squared value, which is 0.47. That's this overlapping region here, basically. Again, you all have done R squareds before in previous coursework, so I'm not going to spend a ton of time on R squareds. That's a fun question, but we're out of time. Okay, so now putting it all together. This is the very last thing we're going to do. Putting it all together here. So we have this box right here. The ANOVA box is asking us, did we do a good job of reducing the error? Have we significantly reduced the error? So this is telling me that we have a significantly better fit with the predictor than we did without the predictor in the model. Our full model fits better than our restricted model. P less than 0.05. This is telling us that 47% of the variance in the number of publications a person has is explained by the amount of time it's been since they graduated with their PhD. Again, these, which I'm going to interpret again for you, this is the B0. So the average person has 3 publications when their years from PhD equals 0. And this is not centered, so years from PhD equals 0 is when you graduate. And this is telling us for every year out of graduate school, the mean number of publications increases by 4.7. And for each of these, you can interpret whether or not this is significantly different from 0. So for this one, the person with publication years since PhD equals 3.107. So that is not significantly different from 0, which means if you don't have any publications when you graduate, it's not different than normal. I hope. Again, this is fake old data, so who knows? I can't find new data. I have tried and tried and tried. I can't find it. All right, so for this one, this is about half a publication every year or 1 publication every 2 years, and that number is significantly different from 0. All right, that's how we interpret that. And now, I'm going to put it all together in one piece. So now we've been focusing on the underlying maths, but I'm going to interpret an entire regression and walk you through exactly what you need to include for any one of these that you do. Here's my example research question. Is the amount that a student studies predictive of their GPA? The outcome in this question is the GPA. The predictor in this question is amount of time studying. When you're approaching a regression problem, which is what you're all going to start to do starting tomorrow, the first thing you need to do is understand the variables in your model. You've already done some of that for your assignment that you turned in today. Second, you'll run the regression, which you'll learn to do tomorrow. Third, I want you to interpret the R-squared, the F-test, the intercept, and the slope. We did all 4 of those today. And so, again, this is just here for your notes for later if you want to come back and look at them. That's how you run statistically in SPSS, how you run this. For my study time, I have 24 cases. That's the first thing I want to know. I have a minimum of 5, a maximum of 18. GPA, my minimum was 1, my maximum is 4. Now I'm going to run the regression. I did not recenter these first, just FYI. You can choose to not do that. You just have to be careful about your interpretations. So I have entered my study time as a predictor of GPA. Now I'm going to interpret my R-squared. So the first thing I get is an R-squared value, 0.73. That is very high. The number of hours or amount of time spent studying in hours is predictive of GPA, and it predicts 73% of the variance in GPA. What does that tell you?
That it's a good predictor of GPA.
It's a very good predictor of GPA. It also tells me that these data are definitely fake. There's no way that that's actually predictive. There's no way. If anything, it might be the opposite. Whatever. I'm sure these are fake. I made these particular slides I made a long time ago, so I don't remember. But it has to be fake. 73%? No way. Okay. So that's our R-squared, 0.734. Here is an explanation of that. We explained 73% of the variance in GPA by including amount of time spent studying. Next, we have the ANOVA table, which is our regression sums of squared errors. That's our how much we've decreased the error in our model. So this is telling me my sums of squared errors of the regression is 15.8 with 1 degree of freedom, because again, that's the difference between our restricted model and our full model. The F-test is 60, and that is less than 0.05. And so here, what I can say is that we have significantly decreased the error variance. And here's my degrees of freedom statement. F equals 60, P less than 0.001. And we get a significantly better prediction of GPA compared to a model that includes just the mean. So either one of these statements is accurate, either one works for interpreting your F test here. You do not have to include both, but one of them would be, using one of them is the way to report it. Okay, B weights, we have talked through this quite a bit, but I'm going to do it one more time for you. In the B weights here, we have a B0 of negative 0.144. That number is not significantly different from 0. That's telling me that the average GPA for someone who studies 0 hours per week is 0.44. It's negative 0.144. Isn't that interesting? Now, that number is not significantly different from 0. This is exactly how you would report on your intercept B weight. You can take my words GPA and hours spent studying and my numbers and replace them with yours. All right, B weights here. Study time is 0.228, so that's for every 1 hour increase in study time, GPA is expected to increase by a significant 0.228. And this is how you would report this t-test. The t equals 7.79, p less than 0.001. Or less than 0.05 is fine as well. All right. So you can interpret it this way. Study time is significantly predictive of GPA. And here I'm putting the b value. So either one of these is accurate. You do not need both. If it was not significant, you would say that study time is not significantly related to GPA. But it is. So you would say that it is because the data are not real. And then this is the regression equation for this model. I'm harvesting this B0 here and this B1 right there. So that's the whole thing in one little package. What's the expected GPA for someone who studies 10 hours per week? You replace this X with a 10 and you would get whatever that is. I don't actually know because I am very bad at math. 2.14? 2.14, I think. Maybe. Okay. For the very last thing we're going to do before you go, this is just an unofficial quiz to just make sure we're getting it all put together. I do have a way for you to do this on Carmen, but what I'd like to do is just have you jot it down here, and I just won't even open the Carmen quiz unless you all want me to, in which case jot it down to me in the chat box. Okay, get a piece of paper. Here's the instructions. Inherent to SPSS is a data set called carsales.sav. It just comes with the stats package. The basic question I have is whether fuel efficiency measured in miles per gallon, is it dependent on whether the vehicle is classified as a car or a truck? That is called type of vehicle in the data set. So I ran a regression analysis with miles per gallon as the dependent variable or as the outcome. And I used type as the independent variable. For the type variable, truck is equal to 1 and car is equal to 0. So I want you to answer, work together with your neighbors. I'll put you in your Zoom rooms and you can chat there. I miss seeing people in person. Okay. Here is my output. Here are the 6 questions that I'd like for you to answer. I have all of this on the Carmen quiz that I will open because then you can see it once the class is over. And I know my plan was for us to be done at 6, and just like last time, I seem to be giving you this quiz at 6 o'clock. So if you need to go, you can totally go and answer these questions later. Otherwise, I'm going to put you in your Zoom rooms and hope you can spend 4 or 5 minutes together chatting through these questions. Before we do that, hold on. I just threw a zillion things at you all at once. So let's take a quick minute. I'm going to give you the last 3 minutes of this class to silently work through this before I let you go into your Zoom rooms. And you can ask me questions through the chat that I can answer in the chat. Okay, so 3 minutes of quiet working alone, and then I'll put you in Zoom rooms where you can stay until you're done for the day. Okay.
Pay attention.
Okay, ladies and jelly spoons, I'm going to open your breakout rooms to go and chat with your neighbors. When you're done, you can come back to the main room and talk to me, or you can vanish off into the wind. I have opened the quiz for you online, so you can look at it, but maybe don't start it yet because I realized I didn't explain which one was, which type was which. So I'm going to add that to the description really quickly before you enter in any answers. If I don't see you back here again, thank you so much for being with me today. I appreciated seeing all of your faces or your names if I didn't see your face. And I'll see you next week. Turn in your homeworks on Friday. Okay. See ya later. Okay, we're just recording me. That's a little funny. Hello, thank you for watching this far into the Zoom session. Two to 12, so 8 equals 7. And then 6. Seven. Hi.
Hey.
You are my randomly selected from my dice rolling app room. How's it going? How are you feeling?
Okay. So question number 1 is about the variance explained. So I thought we need to look at the r squared,
Mm-hmm.
right? So maybe the answer will be 33.1%.
What did you think about that? Is it Alyssa? Am I saying it right, or is it Elisa?
Mm-hmm.
Alyssa?
Yep, that's right. That was gonna be my guess. Yeah. Okay.
Good job.
Yay.
Yay. 1 check.
Check. Okay, so does the full model fit better than the restricted model? Yes, I think so.
Where does that number come from?
Where's the table? Okay, I just looked at the significance value, so it's 0.000. So
So it's less than 0.05. So I thought it's yes. The answer is yes.
Yes, and you pull it from that ANOVA table, the F test.
Yes. Right.
From that ANOVA
The
table. All right. Nice. Okay. How about these other pieces? Was interpreting the slopes, did that make sense to you before in our earlier examples?
In the earlier examples, I wasn't having any trouble, yeah.
Okay. Those middle ones might have been a little weird because of the centering thing.
Yeah, but once, I mean, like the example that we did in the breakout room with, you had the 36 months, I think was your centered. And then, of course, to do the 72, 72 minus 36 is 36. So you put that in place of the 0.
Yep, exactly. Okay. Well then, do you have any questions for me at all before I go to another randomly generated breakout room?
I was a little bit confused about the question of the question. So I mean, when you look at question number 3, interpret the intercept in a sentence. So does that mean that okay, so by the car type, when the type of the vehicle is a car, then the MPG will be 25.297. So that is significant. So
Yep.
it means it's different from 0.
Beautiful.
Okay, that one.
That was perfect. You have all of the pieces in that.
Okay, thank you.
Well done. Yep, that's exactly right. Okay, well, great. I'm going to go visit. Of course, the next one, your group breakout room 7, the next randomly rolled one was 8 because that's how random numbers work. So see you later.
Thank you. See ya.
Yeah, bye.
Bye.
Whoops. Maybe. Okay, now bye. Hi. Oh my gosh, there's so many of you here.
Hi, Dr. Logan. We have a question about question 6. What's the meaning of question 6?
Yeah, we didn't get it either.
Yeah, it was more of a thinking question. I was just asking you, vehicle type is an obnoxious name because you don't know what it means. And I was asking you to brainstorm for me what could maybe be a better choice. What can I put there to make that clearer what it actually is?
Did you end up doing truck and not truck? I guess.
Yeah, I think if it said truck, for example, then I wouldn't have had to go back in and add, when type equals 0, then that means cars, and when type equals 1, that means trucks. But if I just called it trucks, then you'd know it meant when it's a truck. And I brought that to your attention because data management is one of my most favorite things to think about. And because as you're working with your own data, I think you will keep yourself more sane if you are using variable names like truck and not variable names like type, because you'll forget. You think you'll remember, but you will not remember. Guarantee it. I have a very close friend who in his graduate program interpreted that kids who had low birth weight were doing better in life on their vocabulary tests than kids who didn't have low birth weight. And it's because he forgot how he coded low birth weight. He thought one meant yes, low birth weight, when it actually didn't. So you'll forget, and that can be very challenging.
Yes.
That's all. Any other questions? I just went on a data management tangent. Anybody else have things they want to talk about?
Oh, yeah, I also wanted to ask, when you say you're labeling the cars as trucks or not trucks, as 0 and 1 and as dichotomous, does that make a difference when you're saying, with the slope increases by so and so when you go up by 1 unit? So how do you gradate that and say which is 0 and 1? Like, how do you decide which to label?
You get to choose. That is your own choice.
Yeah.
And next week, what we'll do is I will do it both ways for you so you can see how it's different.
Okay.
So you can see that some things will change when you recenter it and some things won't. Now, I did give you a centering example before. All that is recentering, right? So before, a 0 was trucks or was cars. And if I change it so that 0 is going to be trucks, some of these numbers are going to change, but not all of them are going to change.
Got it.
Dun, dun, dun. Foreshadowing. I was an English major before I found statistics. That's a literary phrase. Okay, other things? If there's no other things, I'm going to go drop into another random breakout room. Oh, where'd everybody go? Huh. Okay, I'm gonna jump out of here and come back and see you in a minute. Hello.
Hey.
You are my randomly assigned dice rolled room. How are you?
We're doing well. We just finished number 5.
Yeah. Question number 6 is a weird one. We were just chatting about it in the last room. It was because I wanted you to be thinking about what does a dichotomous variable mean and how is it confusingly labeled. It's nothing that we really talked about.
I see.
That's is what it is. But with the first 5 questions, any of that feel a little bit fuzzy or strange? Can I help talk you through any of that feels uncomfortable?
I feel like the one we kind of like spent a little more time on was the full versus restricted model. Which one's better fit? And we said yes, the full model is a better fit because from the ANOVA test, it's significant. So that means like the residuals, the error is significantly reduced in the full model. So like for the full model, are we looking at like the regression sum of squares and then the restricted would be the total sum of squares?
Yeah.
Okay.
Well, sort of. So the regression sums of squares is the difference between the residual and the total. Wait, I have it pulled up on here. So let me just. So right here, the total is the restricted model. This here is the full model. And the regression is the difference between the two. Remember how when we were calculating the F test, we had the sums of squared errors from the restricted model minus the sums of squared errors from the full model? And all of that was over something else. So this here, that is the difference between these two. If you subtract 18 from 28, you'll get 927.
Okay.
So just like with the coefficients we were talking about before, remember with vehicle type, that's the difference between having a 0 or a 1 for your vehicle type. This is like, is the difference between restricted and full model, is that difference different from 0? That's what the 927 is testing.
Okay.
So you have the answer exactly right. I'm just talking about it some more with you.
Okay. So as long as like, is it usually that the residual will be smaller than the total?
Yes.
Okay.
Here's why. Because remember, the residual is the total, the amount of error still left in your full model after you've used your predictors.
Oh, so you would be only, basically we'd be looking at the significance. So like, if it's not significant, then that means the full is not a better predictor then.
Probably, but also sometimes, most of the time that works out that way, but not always. So, but always when you guess the mean for everybody, you're going to do a terrible job. And that's why that number is always going to be the biggest, this total. This value here is the error in your model once you've included predictors. So you've reduced that error somewhat, and this is the amount you've reduced the error.
Okay.
Okay. All right. I got a request for help in another breakout room, so I'm going to let you all chat about the last. The last question is just a thought question. There's no right answer. It's just pointing out that vehicle type is a crappy variable name because you don't know what it means. And maybe when you're thinking about your own variable names, you can make better choices than this data set did. That's all. Okay. Bye. Ooh. Hi.
Hi.
My internet just shut off for a minute, but I'm glad you're still here.
Oh, yeah,
How
we've
are
been
you?
talking. We're good. How are you?
Great. Did you call me and ask me for help?
Yeah, we
Okay,
did.
good. Just making sure that I ended up in the right place.
Yes.
What's up? How's it going?
We're working through it.
Mm-hmm.
We had our biggest question on the last question, actually.
Yeah, I feel like I should have given a better preamble. So let me talk about the goal of the last question. The goal of the last question is to get you to think about how data are labeled and how that can help or hinder you as you're trying to interpret your data analysis.
Okay.
And so that type is pretty confusing because do you know which one means which? You do, but like how hard did you have to work to figure out which one meant car and which one meant truck? That's all. And so it was just, I wanted you to think through data management of this particular item and how it's scored.
Okay. I think that makes our answer incorrect.
I don't think there's any such thing as an incorrect answer. But what did you say?
So we actually said truck fuel efficiency because the constant would be the car's fuel efficiency because it's always when x equals 0, and the only other value that x can be is 1, which is truck. So therefore, like, the value would be truck fuel efficiency. Like, you either have 25.297 or you have 19.7.
Uh-huh.
So that was our reasoning.
You're right, except that would have been a fine name for this in this case. But if you then later on predict something like the I can't think of what else happens with cars, the weight of the car. That's a terrible example. Horsepower? Is that a thing you'd predict about cars?
Sure.
I don't know. Sure. If you were predicting the horsepower of the car, for example, and you still used car versus truck, then the answer wouldn't be fuel efficiency. The answer would be horsepower. Does that make sense? So you can you would need to make the name of it pretty generic to represent just what that variable represents standalone in your data set entirely. So maybe one of the other breakout rooms I was in said, what if we just called it truck? And I was like, that makes sense.
Okay.
Yeah. Truck, yes, or truck equals 1. Something like that could be helpful to you as you're analyzing these data, because that would make you then go, okay, the difference between someone who's not a truck and something who is a truck is 5 miles per gallon. 5.5 miles per gallon.
Okay.
Oof, you have very somber faces. And it makes me feel like this was fuzzier than I wanted it to be. So what else felt really fuzzy about this piece?
I mean, it was good. I got it came across to me. I was just thinking of those labels here just a minute ago. Like I was thinking like truck characteristics, something along those lines.
Not a car. Yeah, you could call it truck or not car, or type in parentheses trucks. Something like that could work. The reason I brought it up again is for you to think about as you're processing and getting ready to work with your data. If you name something, for example, naming it, if you have a variable that's gender as classified as male or female, and it only has 2 categories, if you include that as a variable and you call it gender, you'll probably forget which one you coded as 1 and which one you coded as 0 or whatever else you coded it as. So changing that around to represent one of those categories can be helpful to you as you interpret them. So if you call it 0, 1, and the 0 is someone who's female and the 1 is someone who's male, then you would maybe name that variable male, because then you know what that contrast is all about.
Okay. So you would recommend naming the variable differently as opposed to using like the label function in SPSS, where like you can just add details.
I don't have a strong preference, but my advice that I try to give is, well, this advice in particular is sort of agnostic to program. The rest of my advice clearly isn't. I'm literally showing you SPSS output tables. But in general, when you're naming variables, no matter what program you're using, you can use this particular trick. It's not a trick, but this rule.
Okay.
Yeah, that's all. But if you got the other 5 and the other 5 are feeling good, that's what really matters for this case. Because those 5 things are what are going to be on your homework assignment.
Okay.
But with your
And
own data.
You said for number 4 with the slope in this case, because it was categorical, you said that like there were 2 sentences provided and we only had to use 1. So like could we just say it's significantly predictive instead of for every time you change to a truck? Because it's kind of hard to say for 1 unit increase.
Yeah. Yep, absolutely.
Okay.
They're significantly related. The other way you could say it with a dichotomous variable is the difference, the expected difference between cars and trucks is.
Okay.
And I think I forgot that I had these last 2 slides. The last 2 slides on the slide show, no, hold on, sorry, I don't know what I'm doing. La, 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 la. The last 2 slides here are interpretation templates? No, explanatory or explanators? I don't know what I'd say. So I have interpretation when you have continuous and interpretation when you have dichotomous.
Oh,
And so
that's helpful.
That I definitely should have pointed out. So I will put that in the announcements to make sure you look at the last 2 slides. So that's sort of the difference between these last 2.
Okay. That's helpful.
If one value of x is 0. Okay. Cool. Okay, anything else?
I think we got it other than that.
Okay.
The non-stats question threw us.
Oh yeah, sorry about that. I forgot. In times past, I have spent a long time discussing the difference between different ways you code 0 and 1 variables, and I just cut a lot of that out in trying to shorten things up and forgot that question was on here. But I still think it's good for you to think about as you move through these questions and your own analyses. Starting tomorrow. Okay, I'm going to leave. I'll see y'all later. Susan!
Hey.
Thanks for waiting.
No problem.
I wonder how many people are still here.
A few like popped in and left and.
Oh yeah, just that one group who I was just with. Cool. I'll let them stay as long as they want. Today was a little better, I think.
Good. It was good.
It was a little better. I'm shocked. I actually almost was just like, forget it. I'm not even walking through the rest of this, but I ended up getting through literally everything. So that's nice. Hi, y'all.
Oh,
welcome. Welcome back.
Hi. Actually, I do have one thing that I noticed while we were working on the slides.
Oh, God.
In my homework, I said P is less than 0.05 for the Shapiro-Wilks coefficients in my table instead of less than 0.001 when it was all zeros. So I do realize that that was a mistake, and I just wanted to say that I noticed that now.
That's totally fine, honestly. And I think I said it, but it was really in passing. But it's however is more comfortable for you to say it is fine. I would recommend when you go to publish things that you use that rule of give the exact p-value unless it's less than 0.001. But in your homework assignments. I'm not going to ding you for that. It's all about practice.
Okay. Thank you.
Yeah, welcome.
Have a good week.
Thanks, you too.
I just wanna ask you something about. I sent you an event for next Thursday at 4 p.m. for our
Yes.
meeting. I don't know if you get it.
Yes, I got it. I thought I accepted it, so it should be. We should be good to go.
Okay, I just want to make sure.
Yes, thank you for double checking, and I am double checking right now also while I'm talking to you. I'll just look at my calendar. Next Thursday, the 17th?
Yes.
Yeah, it's right there. I got it.
Okay, cool. Thank you.
I'll make sure. Here, I'll go hit the accept button.
Okay,
All right, there you go.
see you.
Yeah, see you later. All
Bye,
right, bye.
Susan. See you tomorrow.
Oh, got that. Okay, how did it go with you last week?
Pretty good.
Yeah?
Yeah.
I've only had 2 people reach out to me in the last week to work on their data sets. So hopefully everything went fine. I'm about to go grade everybody's homework ones, so we'll see if they got it.
They seem to understand at the time.
All right. That's good. Yeah, and the one student I know you were working with I think you had 2 that you sent back to me because you were like, this is not going to work. Keep looking. And they both have data now.
Okay.
Let me pull up the homework assignment. I think you have a pretty clear idea of what to work on this time. I think if you use that 5-step thing as a guide, that would be a good start. Where's the ding dang homework? What is happening? Somebody lit a fire in my neighborhood. I smell it. And we're not in California, so I don't think it's those fires. All right. I don't know if you remember this homework assignment. It has not been that long. Okay. This is doing their first regression, and I'm asking them for 3 to 4 sentences of background, their research question, how many participants they have, paste the output from your statistical program, interpret your B weights. I didn't even put the R squareds on there. Whoops. I probably should have. I definitely meant to, since I walked them through that. Actually, maybe let me go pull it down real quick and I'm going to change it. And if anybody turns in the old one, that's okay. Ooh. Okay, I unpublished it, so I'll fix it. And I'm going to follow this exactly. Where'd you go? 5 things. 4 things. R squared, F test, intercept, slope.
Okay.
I'll have them do still the background, the research question, the data, and then we'll have 4 parts of results.
Okay.
And I feel like they do better when I think doesn't work when I do it like this. But if I say, interpret the 2 B weights, what do they mean in the context of your study? If I actually ask it like that, sometimes they answer it. Okay. So I'm going to fix this and then I'll upload it. Does that make sense?
Yes.
Okay. Is there anything else that you noticed? Thank you for being part of those breakout groups. I'm not sure how to make it so that you're not included.
It's fine.
But, does that
centering on me? Yeah. I'll also include.
Oh, good. Oh man.
I was wondering if you want me to do like dummy coding for like dichotomous variables, so like it's 0 and 1 instead of like 1 and 2, that kind of thing.
You can if you think you have time. I think the most important thing is getting
Those
them familiar with all four of these things.
Okay.
R squared, F test, intercept, slope. They've never run a regression before, so they'll have to walk through running a regression. And I think you can tell them that they don't, I will put on here, you don't have to center your variables for this assignment.
All right.
And then we'll have time to work on it next time, because I'm going to dig into dichotomous variables and like variables with 3 as we work on as the intro to multiple regression. So they'll get dummy coding at the beginning of the next session.
Okay, so centering next week.
Yeah.
All right, and then, okay, so simple linear regression, I'll do both point and click and syntax.
Yep.
Then make sure they just know how to read the output.
Mm-hmm.
Okay, that's simple enough.
Yay. I'm always, it's really such a shame. I feel like I'm finally getting the hang of this class and now it's going to go away.
Yep.
You don't need to center your predictors. Center your data. Okay. And then the other thing I'm going to post, I'm really just talking out loud to myself. I'm sorry that you're having to listen to it, is I'm going to post the readings about interpolation. I have one reading. I really love it. It's so fun. It's like, it plots the slopes of male runners and female runners at the Olympics. And based on those plots suggests that at some point in 2040, women will be faster than men.
That's interesting.
And that's how they plot it out. So I think it's a nice example for how can we really interpret this? Is this really what regression is for? So it's a talking topic of just what does it mean to interpret data within the range of your, hopefully that'll get them thinking and talking, and that's what I really want.
That's a fun one. You said it was an article you will post?
Yeah, I'll post it.
Okay.
As part of a discussion thing. I think. I can't decide. It's really hard because I want them to have the ability to talk to each other about the readings, but I don't want to like make them. But if I don't make them, will they not read them? I don't know.
Yeah.
What do you think?
I'm trying to think what my other classes do. I know in measurement, we're made to. So, like, she puts us in small groups, and we have to, like, as a group, say something about the discussion post. Everything else is more individual. So it's make your own post.
Yeah.
And you're supposed to make any kind of post by a certain day and then reply to a post.
Oh my God.
Another day.
I forgot I'm still recording. Stop share. I'll see if I can trim this part off. Sorry.